بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Hello guys, and welcome back to a new tutorial on robot operating system. And this time I'm going to talk about ROS serial. So you may wonder what is ROS serial and how it is important, in which cases we can use it. So basically imagine that you have a new hardware. Imagine that you have, for example, a new sensor or new actuator or any kind of device that you want to add to ROS ecosystem. In this case, you are going to face two situations. Whether this hardware already has a ROS driver, and this means that it is already supported by ROS. So in this case, you can connect it to ROS ecosystem, you run the driver, and then you can get all the information coming from this hardware, and then processing it using robot operating system. That's possible. For example, you can buy a new laser scanner, for example, URG laser scanner or RGB camera like Asus Live Pro or Kinect, and they are already supported in robot operating system. So you don't have to worry about all the problems of how to interface with them, how to get data in your ROS programs, because the drivers are already built for that. However, if you have another hardware that does not support ROS and that you want to use it with the robot operating system, and this is where we have problems. So in this case, we are in front of two different situations. Whether we need to develop our own drivers, and this is actually time consuming and very tedious operation, it takes a lot of time. And actually you need to develop your own interfaces and the message exchange between robot operating system and between the hardware firmware itself. So this is actually time consuming. I remember one time I had a project to integrate a sensor node, that is the Telos B sensor node, and we went through a very long process in order to be able to integrate this sensor into robot operating system. We had to develop the driver in C and then create a particular message type for these sensors in ROS, and finally publish it into the ROS ecosystem. So it was a little bit a long process. So fortunately, the ROS framework already provides a very important framework that solves this problem, and it's called ROS serial. So what is ROS serial? It is basically a protocol that was designed in order to communicate between ROS and a new hardware. Of course, there are different types of hardware that are supported by ROS serial. I'm going to present them, but basically it allows the integration of microcontrollers and embedded systems with ROS. For example, imagine that you have an Arduino microcontroller to which you have attached some sensors, and you would like to access the sensor information or the sensor data coming through the Arduino microcontroller. So ROS serial in this case can play a role. There are different types of embedded devices like embedded Linux and other microcontroller boards. So instead of defining yourself the hardware drivers, the message serialization, and all the communication protocol, everything was already done in ROS serial, and this will simplify a lot the integration of this new hardware into the ROS ecosystem. So basically, ROS serial allows a new electronic hardware to directly talk to ROS system natively. It means you can even run the ROS command inside the hardware itself, and you do not need to develop your custom drivers and communication protocols, which is basically time consuming. Also, ROS serial is a protocol that wraps standard ROS serialized messages and multiplexes multiple topics and services over a character device, such as a serial port or a network socket. So this means ROS serial provides all the necessary message serialization to be exchanged between the ROS system running in your embedded device and also the ROS ecosystem that is running on your computer machine. Of course, ROS serial can be applied to a certain number of embedded devices, not any kind. There is a general ROS serial client library, okay, and this library is the general client-side ROS serial implementation that was designed for general microcontrollers and can run only on any processor for which you have an ANSI C++ compiler and a serial port connection to a computer running ROS. So basically you can use ROS serial client for any kind of microcontroller with the condition that it has ANSI C++ compiler. But also there are specific ROS serial client libraries for particular embedded systems. For example, there is ROS serial client library for Arduino, and it is called ROS serial Arduino. There is ROS serial for embedded Linux. There is ROS serial also for Windows platforms, for Embed, TiVac, STM32, and Teensy. So these are the main embedded system platforms that have their proper ROS serial client libraries. In this tutorial, we're going to present ROS serial Arduino. So I'm going to show you the full process on how to install ROS on an Arduino system and how to connect it to a ROS ecosystem that is running on your computer. On the other side, we need to have ROS interfaces in the computer machine that is running the main ROS ecosystem. So this is actually the architecture. You have a new microcontroller, let's say you have an Arduino, and you have also a computer that is running ROS, and then you connect using a serial connection the Arduino system to the computer, okay? So we're going to install ROS serial Arduino into the microcontroller so that we can run ROS commands inside. For example, we can run publisher, we can run subscriber. I'm going to show you different examples on how to run ROS serial Arduino in an Arduino system. And on the other side, we must have a special node running that will actually make the interface between the ROS serial Arduino and the ROS ecosystem. So ROS serial Python is a Python-based implementation. It's going to be like a server running in the computer machine that is going to receive all the ROS messages coming from ROS serial Arduino, the ROS serial client application, and then we'll relay them with the remaining ROS ecosystem. In the same way, there is also an equivalent C++ implementation which can also be used, which is called ROS serial server, which has some limitations as compared to ROS serial Python, but it is recommended for high performance applications. So basically, the most recommended ROS serial interface is the ROS serial Python. It's easy to use, and it will represent like a gateway between the embedded system device and also the ROS ecosystem. So just to summarize, ROS serial is a protocol that allows the communication between embedded devices and the ROS ecosystem. So basically, in the embedded device that we can program in a C language, we're going to install a ROS library. For example, in case of Arduino, we're going to generate a ROS library specifically for Arduino systems, and you are going to integrate it into the Arduino integrated development environment. And then we will have the ROS serial Arduino that will be running on this device that will be able to publish ROS messages, okay, which will be received by the ROS serial Python, which is a local server running in the ROS ecosystem that will receive the messages and then dispatch them to the remaining ROS ecosystem. This is the general architecture of ROS serial applications. In the next video, I'm going to provide a brief overview about the Arduino technology, and then I'm going to illustrate through examples how to run ROS serial Arduino and how to communicate an Arduino device with robot operating system. So let's get started. Arduino Uno. Basically, the differences here is in terms of microcontrollers or the amount of memory available. So it depends on your requirement. You may choose one board or the other. Some sensors or application may be more adapted for one board than the other. So in principle, when you want to start an Arduino project, you need to carefully choose your Arduino board. But for entry level, for simple prototyping, basically the Arduino Uno is the most popular platform that is actually used by beginners. There are some other boards with enhanced features. For example, Arduino Mega, it has much more memory, up to 256. So if you are interested to know more details about any of this platform, you can go its datasheet, and it provides all the specification for the Arduino board. Some other boards are also built for Internet of Things application. For example, Arduino Ethernet, it has an Ethernet port available which allows the board to communicate with the Internet through a local area network. Arduino Industrial, there is also a GSM board, another board that allows to communicate through Wi-Fi. So basically, these IoT platforms, they have different types of communication interfaces allowing them to connect to the network and communicate with other devices. So when you use Arduino boards, you need to use also some other sensors. And there are many types of different sensors. For example, you can have barometer for altitude measurement, temperature sensors, passive buzzers, the sound sensors, LED sensors. There is also different types of gas sensors for air quality monitoring, ultrasonic sensor for range measurement, obstacle avoiding sensors, color sensors, button sensors, buzzers. So these sensors can be easily integrated and connected to the Arduino board on specific pin numbers, and then using the Arduino IDE, it is possible to read the information coming from these sensors and then perform required processing based on the application logic. In our demonstration later on, I'm going to show you how to work with an ultrasonic sensor to estimate the range to an obstacle. So I will show how to connect the ultrasonic sensor, how to develop an Arduino program to read the information coming from the ultrasonic sensor, and then how to use ROS serial in order to connect this ultrasonic sensor to a ROS ecosystem that is running on a computer. In this video, I'm going to present the main properties of the Arduino Uno board. Arduino Uno is a microcontroller board based on 8-bit Atmega 328P microcontroller. It also has other components such as crystal oscillator operating at 16 MHz frequency, serial communication through USB port, a voltage regulator to regulate voltage at 3 or 5 volts, and many different input-output ports. Arduino Uno has 14 digital input-output pins, out of which 6 can be used as PWM outputs. It also has 6 analog input pins with ID from 0 to 5, a power barrel jack that receives an input voltage of 12 volt, and an inserted serial programming header and a reset button. There are 2 types of sensors that can be used with Arduino Uno board. Some sensors provide digital data, and some other sensors provide analog data. Digital data sensors should be connected to the board through the digital input-output pins, and analog sensors must be connected to the board through the analog pins. Every pin has a number, and this number allows to identify the signal pin in the programming environment through which the data will be received from the sensor. This makes it so easy to interface with any sensor in the programming environment. What you observe in the top is called the Arduino base shield. The shield can be mounted on top of the Arduino board to be able to connect sensors through it, using 4-pin I2C connectors. This is the Arduino base shield version 2, and this is the 14 connector. And you can observe that the base shield has several inputs. We have digital inputs, D2, D3, D4, until D8. We have I2C inputs, and also we have analog inputs. It's possible also to configure the base shield whether to operate at 5 volt or 3 volt using this switch. This is the reset button here, and it has also a UART interface. The base shield is very useful to connect multiple sensors to the Arduino board. In the next video, I will show a sample program using the Arduino IDE and demonstrate how simple it is to develop a program that interfaces with sensor. Before moving to ROS serial and how to develop programs for Arduino, I'm going to introduce the Arduino Integrated Development Environment, which is the development environment that is used to develop programs for Arduino boards and systems. So in these slides, I provide a very simple example of a temperature sensor. What you can see here in the right side, we have an Arduino board, and here we have a temperature sensor that we will connect to the Arduino board. Okay, so as you can see, we connect the red wire to the 5 volts, we connect the black wire to the ground as usual, and here we are going to connect the signal wire, the blue one. It's the wire that is going to transport the signal that will provide the temperature information, the port number 0 here. And here we have an analog sensor in this example, so it's going to be connected to the analog pin and with index 0. Now in the left side, you can see the Arduino Integrated Development Environment, and later on I'm going to tell you how you can download this from the internet, and I'm going to show you some real case demonstrations, but I would like just to explain the structure and the skeleton of an Arduino program. So for this one, we're going to develop the following Arduino program. And before starting talking about the details, something that you have to know is that the Arduino, it has 2 main important functions. The first function is called setup, and this function is used to initialize the parameters of the connection, for example, the serial connection, baud rate, and any information or any variable that you would like to initialize is going to be initialized in the method setup. So setup is only executed once and only one time, just when the program starts. After being executed, the program will never come back to the setup function, only if you reset and restart your program from 0. Okay, after that, the program is going to move to the second method that is called the method loop. And this method loop is going to run forever. This is like you have an endless loop condition. For example, it's like you have while true, and it's going to loop forever here. Okay, this is the structure of Arduino programs. So all the application logic must be defined in the method loop. And of course, setup and loop do not take any parameters. Here, as you can see, we're going to define a constant variable that is called sensor pin, and in this case, the sensor pin is going to be equal to 0. Why it is equal to 0? Because the signal wire, that is this one, is connected to the pin number 0. If, for example, we have connected it to 1 or 2 or 3 or 4 or 5, this number should change to be exactly the same as the pin connected from here. And then since we are connecting to an analog input, so we're going to use the analog read method on the pin number 0. So remember that sensor pin, it refers to the constant 0 here. And this reading is going to return a value between 0 and 1 that we need to convert to a voltage. So the voltage will be equal to 5 volts because here we assume that we use 5 volts. If we use 3 volts, we need to multiply by 3. So if we use 5 volts, as you can observe here, because the wire is connected to the pin of the 5 volts, this is the power wire. Okay, we calculate the voltage, then we divide by 1024. And this is actually the formula that is related to this temperature sensor. Every sensor actually, you extract some raw information and then you process this raw information to extract the real temperature. Okay, and then after some processing, okay, depending on the information extracted from the sensor, so here we can extract the temperature in Celsius, and also we can convert the temperature into Fahrenheit, and finally we use serial.print to print and display the information both in degrees and also in Fahrenheit. So this is a very simple program, and every Arduino program is based on the same structure. And if you have any other sensor that you would like to use, basically you can look into the internet and you will find existing code that you can integrate into your application. For example, I'm going to show you, if you want to program an Arduino program for a gas sensor, you can do Arduino gas sensor, okay? And here you will find documentation. Of course, there are different types of gas sensor. There is MQ2, MQ5, for example, let's say MQ5 or MQ3, okay? So you will find so many websites, okay, that presents for you all the information about the sensor. And usually at the end, you will find code, okay? So this is how to connect the sensor using the base shield to the Arduino board. And then you will find a sample code that you can use. Okay, just you need to copy paste this one. So this one is also operates on the analog input. So it's going to be connected to A0. Okay, and you can integrate. You can just follow the instructions and integrate this into your program. And you can do the same for any kind of sensor depending on your application. So this was an introduction on the Arduino IDE. In the next video, I'm going to develop an application that uses the ultrasonic sensor to find the range to an obstacle. I will start first by showing you how to download Arduino IDE into your environment, and then how to write a program for the ultrasonic sensor. First of all, we're going to write the program just using purely Arduino, and later on we are going to integrate this program into the ROS ecosystem using the ROS serial. So let's make it work. In this video, I'm going to show how to install the Arduino integrated development environment so that later on we will use it in order to develop a small program with Arduino. The process is very simple. This is the link of the website from where you can download the Arduino IDE software. As I already mentioned, Arduino is a cross-platform, so you can install it on any operating system, including Mac operating system, Windows, and Ubuntu. Since we are going to work with Arduino and integrated with ROS, so we need to install it in our Ubuntu operating system where ROS is installed. So let's see how it works. Now I move back to my Ubuntu virtual machine where I have ROS installed, and this is the software download website. You can download the latest version, and currently the latest version is Arduino 1.8.6. So you can download it for different operating systems, whether for Windows, Mac operating system, and Linux operating system. So in our case, we're going to choose Linux 64 bits. Just need to click here and then download the software. The file will be saved into the download folder. It takes a little bit of time to install. And now it's done. You can go to the download folder, and then what you need to do is just to extract the zip package like this, okay? And finally, copy the zip package into the home directory. Now I have it here into the home directory. It's called Arduino 1.8.6. Okay, this is the Arduino source folder. Okay, we have the Arduino executable that we are going to use to start the Arduino integrated development environment. And here we have different other folders. So in this folder, it has several examples that we can access from the integrated development environment. And also here we have some libraries, and this is where we are going to add the libraries related to robot operating system at a later stage. In order to start Arduino, you open a terminal and then you need to go to the Arduino folder. Okay, so here we have Arduino and you can see now we have an executable. So all you need to do is to do /Arduino and the IDE will open. So these are different programs. So we can go here to the examples. So these are the examples that I have shown to you before. Okay, you can add more examples. So in the next video, I'm going to show you how to write an Arduino program for an ultrasonic range sensor. Now that we have installed Arduino Integrated Development Environment, we are ready to start developing our first program with Arduino. I'm going to use the ultrasonic range sensor in this example, and ultrasonic sensor devices allow to estimate the range to obstacles using ultrasound signals. Let us first understand how an ultrasonic sensor works. The ultrasonic range sensor has two transducers, which are microphones used to send and receive pulse signals. The first transducer will send a pulse signal by sending a low signal first, which is 0, then a high signal, that is 1, and then a low signal, that is 0. And when this signal hits an obstacle, it is going to bounce back and be received by the echo microphone. The sensor will then estimate the distance to the obstacle by measuring the duration between sending the high pulse signal and receiving it back by the echo receiver. The time calculated is the round trip time to the obstacle, which will be divided by 2 to have the actual duration in one direction, and then it will be multiplied by the speed of the sound in the air, which is 340 meters per second. And that's all. The process is repeated and ranges are measured periodically every certain number of milliseconds. Ultrasonic sensors can be used in many applications, such as presence to detect intruders, level of a container, for example, smart containers, or water level measurement, position and distance. They are also called proximity sensors. I want also to attract your attention that there are different types of ultrasonic range sensors in the market. The first type is the HC-SR04 sensor, which has 4 pins. The left pin is for power supply, VCC. The right pin is for the ground, and the 2 other pins in the middle are for the signals. The 3 pin is responsible for sending the high pulse signal, whereas the echo pin is responsible for the reception of the echo after it bounces back against an obstacle. The pin order may change from one manufacturer to another, but in total, we have 4 pins where 2 different signal pins are used, one for sending the pulse and the second is for receiving the pulse. The second type is the parallax pin sensor. It has only 3 pins, one for VCC, one for ground, and only 1 pin for signal. It's called SIG. The same signal pin will be used for both sending the pulse and also receiving the echo. So it will alternate between 2 states. We will be using this type of sensor in our demonstration and implementation, and you will figure out later on how the same pin can be used simultaneously for sending and receiving. On the right side of the slide, the exact sensor that we will be using in the implementation is shown, but you can observe that it has 4 pins, although it is a pin-like sensor, like this one. So we can observe that it has a ground pin and VCC pin in the left side, and then it has the NC pin that is not used for any signal, and we have here the SIG pin on the most right side, which is used for both sending the pulse and receiving it back. We will be connecting this pin to the digital input-output pin number 7 for sending and receiving pulses. Let us see how to connect these sensors to the Arduino board. So basically the connection schema will be as follows. We will have an ultrasonic sensor that will be connected to an Arduino Uno board. So as you can see, we connected to the 5-volt power to the ground, and the signal will be connected to a pin here. So we're going to choose pin number 7. You can find more detail about this sensor, which is called the PIG sensor, in this website, arduino.cc/en/tutorial/ping. So if you want to reproduce the experiment, these are the required devices that we will use in this experiment. Okay, first of all, you have an Arduino sensor board. this one. And we have an Arduino sheet that we are going to use to connect the sensor. It is going to be attached to the Arduino Uno. And then we have the ultrasonic range sensor. Okay? This is the 4-pin connector and a USB cable to connect the Arduino board into the laptop. So this is the ultrasonic sensor that we are going to use. So as you can see, it has 4 pins, okay, and one for ground, that is the one on the left side, then VCC, then NC, and this one is not used, and then we have the signal pin. Okay, so the signal pin is going to send an echo signal, and then it will receive back a response that will be used to calculate or to estimate the range to an obstacle using the sound signal. Okay, so in order to make the connection, first of all, we need to put the shield on the Arduino Uno, like this. Okay, so we connect the shield to the Arduino Uno. And then we use the 4-pin connector. Okay, and we plug it here to the sensor. So you can see that the yellow wire, okay, corresponds to the signal. And then the red wire corresponds to the VCC, and the black wire corresponds to the ground pin. And then here, and since we are going to use the pin number 7 of the connection, so I'm going to put it here in D7, because this is a digital sensor. So I'm going to put it here in D7. Okay, and you can see that this wire, the yellow wire, corresponds to D7. Okay, so this is the pin that will be used for the signal. We will see later on how to use this pin in order to program the ultrasonic range sensor to estimate the distance to an obstacle. And finally, we need to connect the board, the laptop, like this. So after making the connection, we are now ready to program the Arduino Uno for the ultrasonic range sensor. And this is actually the page that we use as a reference for our program. We're going just to use the same program as here. So let me open the Arduino. Okay, go into the Arduino folder, then /Arduino. We can find the example of the ultrasonic sensor here. So we can go to sensor pin. Okay, so this is the same code that you can find in the tutorial, which can be also found here. Sensors pin. So this is pin.ino, the Arduino program that we will be using now. So let's see the structure of the program. First of all, we define a constant for the pin number, and here in this example we have used pin number 7, and then we initialize the serial communication using serial.begin and to specify here the baud rate. So this is going to specify what is the speed of the data that will be exchanged through the USB port between the Arduino board and also the computer. In this case, the baud rate is 9600. After initializing the Arduino program, then we go to the loop method, which will implement the logic of the application. First of all, the signal pin is going to be configured to be used as an output pin because it's going to send the chirp signal. Okay, and this is now the structure of the chirp signal. We're going to send low pulse, then high pulse, and then low pulse. After sending this signal, the pin is going to be converted into the input mode. So the same pin is used to read the signal from the pin, and the high pulse, whose duration is the time in microseconds from the sending of the pin to the reception of its echo of an object. So this high signal is going to bounce back and then will be captured by the echo transducer, and based on this we are going to estimate the duration, which represents the time from sending the high pulse until the time of receiving back the high echo. And using the duration, we can then estimate the distance either in inches or in centimeters. Okay, so here you can find there are two methods. One that converts the microseconds into inches, and this is done by dividing the duration by 74 and 2. And you can also estimate the distance in centimeters by dividing it by 29 and 2. So for example here, this is because the speed of the sound is 340 meters per second or 29 microseconds per centimeter. So the ping travels out and back. So to find the distance of the object, you take half of the distance traveled because there is a round trip time when it goes and return back. So this is why we need to divide by 2 here and here as well. And this value 29 is related to the speed of the sound in the air. Okay, so now everything is fine. We first compile the program, so now you can see that the compilation is done. And finally, we will upload the program into the Arduino board. So you can see here that we have an error message that it cannot find the device TTY ACM1. So first of all, you have to make sure that the Arduino board is connected to your Ubuntu operating system machine. We have to select the board being Arduino Uno. So you can see there are different types of Arduino boards. In our case, we are using Arduino Uno. So we have to select this one. And the second step is to find the port. So here we couldn't find any port for the Arduino Uno board. I'm going to reconnect it again. And then, so I have this connection box. And I will say connect to Linux. Once I do this, I can go back to port, and now I will find that the Arduino board is connected on the port /dev/TTY ACM0. So this is Arduino Uno. I have to select this one, and at this time I am able to upload the program now to the Arduino board, as you can see. Okay, so the program now is uploaded. And now we can use serial monitor in order to see the messages received from the Arduino Uno board. Okay, so here when we use serial.print is going to print them to the serial monitor. So as you can see here, this is the ultrasonic range sensor, and you can observe as I am approaching the sensor, the distance is going to decrease. Okay, so now 1 centimeter, 6 centimeters, 4 centimeters, 3 centimeters, and so on. So now I'm going to go away from the sensor, and then you can see that the distance is going to increase gradually. Okay? So you can see now the ultrasonic sensor is working pretty much fine, and is now finding and estimating the distance to the obstacle. Of course, now we are able actually to read the sensor values using the serial monitor, but we cannot actually read the values from ROS. And this is why we will use ROS serial in order to be able to get the information from the laser sensor directly into the ROS ecosystem. Okay, so you can see now the Arduino board is not connected to the ROS ecosystem. There is no connection between them. And in the next video, I'm going to show you how to use ROS serial in order to connect the Arduino board to the ROS ecosystem and start receiving the range information estimated by the sensor as ROS messages. Now it is time to install ROS serial libraries, and this will be done in 2 steps. First of all, we need to install ROS libraries into the robot operating system itself, and then we need to generate ROS libraries for the Arduino embedded system. Okay, so let's see how it works. So this is the reference page for the ROS serial protocol in the ROS wiki, which is available in the website wiki.ros.org/ROS serial. So you can have here more information about the different libraries available, the specification of the protocol itself, and also you can access the tutorial page for the ROS serial Arduino, which we are going to demonstrate in the following videos. So the first thing we need to do is to install Arduino, and this was already done, but also we need to install ROS serial software. So as already mentioned, the first step is to install ROS serial into the ROS workstation, and this is done using sudo apt-get install ROS, and here we use ROS schematic version, ROS serial, and Arduino. Okay, I have already installed in my system, so nothing is going to happen, but if you don't have it on your system, it's going to install it. And then we have to also install ROS serial itself. Okay. The blind level. I have also already installed in my system. So after doing this installation, we are able to have access to the package ROS serial Python, which represent the server in the workstation side that is going to intercept messages coming from the embedded system. Now, the second step is actually to generate the ROS libraries for the Arduino embedded system. Now, looking at the Arduino folder, if we go to libraries, okay, these are the available libraries for the moment. We don't have any library related to ROS. So we need first to generate this library and then put it inside this libraries folder. So the way to do it, we need to go to the Arduino folder, then to libraries. Make sure that we don't have any ROS lib folder here. We don't have any library for the moment, and then we're going to use ROS. Okay, let's run ROS code at another terminal. Okay, to run the ROS ecosystem. And then inside the libraries folder, we will run ROS serial Arduino make libraries.py. And here we have to specify the location. So the dot here, it means the current location. And then it's going to generate for us all the libraries needed to program with ROS into an Arduino board. So let's look now at the libraries folder. Now we have a new folder that was added. It's called ROS lib, and this ROS lib, it represents the whole ROS ecosystem adapted for the Arduino platform. Okay, so you can see now these are the headers files for robot operating system, and you can have different type of messages already supported in Arduino, like Turtlebot theme messages, TurtleScene, version nodes, all the different packages were now adapted for the Arduino platform. Okay, by doing so, now we have ROS already integrated into the IDE of Arduino, and now it is possible to develop ROS program adapted for the Arduino platform. And now we can open Arduino, and you will see here in examples, we have examples integrated for robot operating system, and in the next video, I'm going to start with the Hello World example. So at this stage, we have everything done in order to develop ROS program for the Arduino platform, and then connect it to a ROS workstation. In the next video, I'm going to show how we can upload ROS programs into Arduino and how to run them using ROS in the workstation. After installing ROS serial into the ROS workstation and also generating the libraries for the Arduino platform, now it is time to run our first program. And like in any programming language, we start by the Hello World program. So let's see how it works. So to start the Hello World example, let's start Arduino, and then we go to File, Examples, ROS lib, we will find the Hello World application. So you will see this is actually exactly the same as any ROS program in C language. Okay, so we include the ROS library, ROS.h, and this is standard messages, string.h. And this program is going to behave exactly the same as the Torque ROS node that we have already introduced in the first lectures of this course, the Torque application, where the node will publish string messages. So we need to include standard MSGS string messages. We create a node handler, and then we create the string message. And this is the creation of a chatter publisher with topic chatter and the string message to be sent. So in the setup function, we're going to initialize the node using nh the node handle.init node. So this is the method that is used to initialize the nodes in Arduino platform. And then we will advertise our publisher, that is here the chatter publisher. After doing the initialization, so we're going to loop forever, and every time we're going to assign the data field of the string message, the message hello world that we have created here as a string of 13 characters. And then we will use the method publish of the object chatter in order to publish the string messages. So the string message is going to contain always hello world and will be published every 1 second. So this is 100 milliseconds. And then we use nh spin once in exactly the same way that we do for traditional ROS applications. So let me now connect the Arduino board to our workstation, and then I can upload this program. So first of all, I need to check. Okay, so we have the Arduino board connected in the right port. I'm going now to upload the program. It's now uploading. Now the uploading is complete. And the next step now is to actually see these messages in the ROS ecosystem. So let's do ROS now. ROS code, it's already running. So if I do ROS topic list, there is nothing. Of course, in order to communicate between the ROS program that I have uploaded into the Arduino board and ROS, I need now to run the server application. So remember the architecture of ROS serial. We have already now uploaded the ROS serial Arduino program into the Arduino board, and it's now sending ROS messages to ROS ecosystem, which is running here But what is missing? We need now to start the server application. So we're going to start the server application using the Python-based implementation with the Rust serial Python package. So let's see how it works. In this case, what we can do rust run, Rust serial Python, and then serial node.py, and then we have to specify what is the port number to which the Arduino board is connected. So here we have /dep/pty. In our case, it is pty ACM0. I'm going to use the same port number, ACM0. And now it is connecting. Set up publisher on Chatter. So it's already connected that there is a Chatter publisher. And then let us now do again Rust topic list. And we find that we have a Chatter topic. We have Coscore running in this workstation, but from where this Chatter topic comes, it comes from the Rust serial Arduino. So I can do Rust topic echo /chatter. And now I'm receiving hello world. It's the same message that is being sent by the Arduino node. You can also do Rust topic info /chatter. Okay, it uses standard message string, and the publisher is the serial node. Okay, the serial node, because we have connected to it using the serial node. Okay, so the serial node is the interface between the Rust serial Arduino that is already deployed in the Arduino platform, and also the Rust ecosystem that is running on this workstation. So this means at the end, the Arduino platform can act exactly as a Rust node. Okay, you can see also some details about the Hello World application, and there are several more tutorials on the Rust serial Arduino /tutorial page. In this video, I have presented how to make a Rust publisher in Arduino. In the next video, I'm going to present how to write a Rust subscriber in Arduino. In this video, I'm going to present the Blink application and how to write a Rust subscriber in Arduino. So let's see how it works. I'm going now to present the Blink example, which shows step by step on how to write a subscriber. So in this tutorial, we have presented how to create a publisher. We can also create a subscriber inside a Rust serial Arduino board. So let's open the sketch of the Blink application, which creates a subscriber. And here in the same way, we're going to include the Rust libraries. We have the node handle here, and we will create a subscriber, which is a template. It takes an empty message, and here is going to subscribe to a topic that is called toggle LED. So whenever an empty message is received on this topic, in this case, the callback function message CB is going to be executed, and what it will do is going just to blink the LED. Okay, so the LED is located in the pin number 13 on the Arduino Uno board, and this operation is going actually to toggle the LED sometimes on and sometimes off. So let's upload this sketch into the Arduino board. Okay, usually when you have this kind of error, it's better that you reset your connections. So I'm going to close everything to reset the connection. Let me start again the Arduino. Now I open the Blink application again. So let me see if it uploads. You have to check the port number. So now you can see now when I have reconnected with them, the port number has changed. Now it is /dev/pty ACM1. So I'm going to select this one and then upload it again. Now it is uploaded. So let's do the same steps. We run Rust core, and then we will run Rust serial Python serial node. So now the port has changed. Instead of /dev/tpy ACM0, it is now connected on /dev/tpy ACM1. Okay, it is now connecting. You can see now it has detected that there is a subscriber on the topic toggle LED. We can use Rust topic list, and we have the topic now toggle LED. So now I'm going to use the command Rust topic tab toggle LED, where I'm going to send an empty message, standard MSGS empty. Okay, and you will see now when I'm going to send this message to the Arduino board, the LED will be now toggle and will be switched to on. So you can see now the LED has actually put on. Now if I publish the same message again, you can see now the LED has switched off. So you can see it's possible to send ROS commands in order to switch on and off the LED. And you can see now there is clear communication between the ROS ecosystem in the workstation and also the ROS ecosystem that is running on the Arduino platform. Okay, so we have used the subscriber in this Arduino Uno platform so that when there is any message coming on the topic toggle LED, the LED will be toggled, switched between on and off. So in the next video, I'm going now to present how to develop a ROS program in Arduino in order to read the information coming from the ultrasonic sensor and publish this information into the ROS ecosystem running on the workstation. In the previous video, I have introduced how to create and execute ROS nodes into an Arduino Uno board. The first example presented a simple talker application that publishes string messages, and the second application subscribes to a topic to control the on-off switch of the LED of the Arduino Uno board. In both cases, the server in the package ROS Serial Python was used as a bridge between ROS Serial Arduino running on the Arduino board and the ROS ecosystem running on the workstation. In this video, we will develop a more elaborated example that uses the ultrasonic laser scanner that estimates the range to an obstacle and then publishes it to the ROS ecosystem. Let us look at the architecture of the application. Our starting point will be the Arduino code that we presented earlier and that allows to estimate the distance to an obstacle by using the time of flight information. Then after we estimate the value of the range, we put it inside a ROS message and publish it through a ROS topic to the ROS ecosystem via the ROS Serial Python bridge. While it is possible to transfer the message as a single value or as a string value, we will use the predefined ROS message for ranges that is called the sensor MSGS range, which is a specific message that carries out range data, not only the value of the measurement range, but also other metadata about the sensor. Let us look at the structure of this ROS message. You can look at the documentation of this range message in the documentation website of the ROS framework. Like any other ROS message, the range message has a header message that defines the timestamp and some other parameters. It also has a field of the radiation type, which can be 0 for sound and ultrasonic sensors and 1 for infrared sensors. In our case, we will use the value of 0 as we have an ultrasonic sensor. The sensor message also defines the field of view, that is the size of the arc that the distance reading is valid for. In our case, we only have one measurement, so we can put any value as it is obsolete for our ultrasonic sensor. The range message also defines the minimum and maximum ranges, which are characteristics of the ultrasonic sensor and differs from one sensor to another. In our case, we will use 2 centimeters as a minimum range and 1.5 meters as a maximum range. Finally, and most importantly, the value of the range, which is the value estimated using the Arduino program that we presented earlier. For every new range measurement, we will update the timestamp of the header and the range value measured. All other values, like minimum range, maximum range, field of view, radiation type, are static and do not change from one measurement to another. Now, having understood the principle, let's see how it is implemented and executed. First, let us open the Arduino. And then we open the ROS Arduino sketch that determines the range value and publishes it as a sensor MSGS range ROS message, which is this program. So this is the code I have written for this purpose, and you can get it from the GitHub repository. The structure of the code is similar to any ROS program running on a workstation. First, we include the libraries, and here specifically, we include the library sensor MSGS/range.h, which contains the specification of the range sensor. This message is defined in the folder Arduino libraries, ROSLib, sensor MSGS, and here we have range.h. As you can observe, the range.h file defines a class for the message range, which contains all the attributes I have presented earlier. including the header, the radiation type, the field of view, the minimum range, the maximum range, and the range value. This class will be used to create range messages in the Arduino program. Let's go back to the Arduino program for now. After the inclusion of the libraries, we declare the node handle that will be used to create a ROS Arduino node. Then we define the message range MSG from the class sensor MSGS range. Also, we create a publisher object pubRange that will be used to publish range ROS messages on the topic /ultrasonic_range. The constructor also takes as parameter a reference to range message created. We define the frame ID needed in the header part of the message. The frame ID is made equal to ultrasonic. We will talk more about frames when we present the TF transformation in a later video. For now, it is not necessary to know the detail. As the ultrasonic sensor will be connected to pin number 7, we create a constant pin assigned to the value of 7. Then, two Boolean constant values, centimeters and inches, that will specify whether the distance should be estimated in centimeters or in inches. The initialization occurs in the setup function. As usual, we initialize the node using init node, and we advertise the publisher to the ROS master node. Then, we define the static parameters of the range message, which are metadata about the range sensor. The radiation type is set to the constant value sensor MSGS range ultrasound because we are using an ultrasonic sensor. The frame ID is set to the frame ID value that we defined above, ultrasonic. We provide any fake value to the field of view as it is obsolete in our case, as I explained earlier. Also, we set a value of 2 centimeters for the minimum range and 1.5 meter for the maximum range. All these parameters defined in the setup function are static in the sense that they do not change over time. The next function is called getRange, which basically implements the same algorithm for range estimation that we have presented in the lecture talking about programming a range sensor with Arduino. Remember that the concept is to send a low, high, low sequence of pulses through the signal pin configured as output, then listen to the echo response in the same pin configured as input. Based on the round trip duration, we estimate the distance traveled, which also refers to the range to the obstacle. The distance is then implemented in centimeter or in inches. Finally, the loop method is very simple and implements the logic of the application. First, it updates the value of the range ROS message with the last measured estimated distance. It also updates the timestamp field with the current time. And finally, it publishes the range ROS message and spin once and repeats the same process every 500 milliseconds. Let us now upload this code to the Arduino board. The code is now uploaded and the port is /dev/tty-acm0. We can verify that the range message published by the Arduino board can be seen by the ROS nodes running on the workstation. Let us first run ROS core. Then we can run ROS topic list. And you can see now we have only 2 topics, ROS out and ROS out app. We don't have any topic for the moment related to the ultrasonic sensor. Like we did before, we need to start the ROS serial server by running the command rosrun rosserial python serial_node.py /dev/tty-acm0 because this is the port to which the Arduino board is connected. Now the server was started and you can see the published range messages. Again, let's try ROS topic list. You can now observe the topic /ultrasonic range that was defined in the Arduino program. Let us see the information of this topic using the command rostopicinfo/ultrasound range. And here you can see that the publishing node is serial node and the type of published message is the sensor MSGS/range, which is the message type that we have used in the Arduino ROS program. Finally, we can run the command rostopic echo/ultrasound_range topic, and here we can find the range value. So observe that the range value is now 17-18 centimeters. I'm going to go closer and closer, and you can see that the range value is going smaller and smaller. And now I will take the obstacle far away, and you can see that the range is becoming bigger and bigger. So it is increasing or it is decreasing based on the distance to the obstacle. You can see from the range value that we are able to get the ultrasonic range in the ROS ecosystem. Congratulations! Now you know the whole process and the workflow to deploy any Arduino board with ROS, and you can collect any kind of sensor data. Of course, if you use different sensors, you need to use different sensor ROS messages. You can check whether there are existing sensor ROS messages already defined and that meet the requirement of the sensor data to be carried out. Otherwise, you can create your own custom ROS message and use them to transport data. Otherwise, you can create your own custom ROS messages and use them to transport data between Arduino and ROS. The other process is exactly the same as it was presented in this lecture.